guys, in this video we will discuss about some theorems on subspaces. As you see in our previous lectures, we have discussed the definition of subspace, and we already discussed several types of subspaces with the help of examples. So now we will discuss some theorems on subspace. So let us begin with the theorem 1, which says that the intersection of two subspace of a vector space is again a subspace. So let's see the proof, how we will prove it. Suppose we have two vector subspaces W1 and W2 of a vector space V. We have to show that W1 intersection W2 is again a subspace. So, and we know that how to prove a subset of a vector space is again a subspace. So first we will see that this intersection is non-empty, because W1 and W2 are subspaces of V. So at least we will have zero element in W1 and W2. So we can say that this 0 is in W1 intersection W2. So we can say that this intersection set is non-empty. Now we will see that this W1 intersection W2 is closed with respect to addition and scalar multiplication. So what you do, take any two elements in W1 intersection W2. So they are in intersection, it means these elements will be in W1 and W2. And we know that W1 and W2 are subspaces of V, so it means their addition must be in W1 and W2 by the property of subspaces. Because their addition in W1 and W2, so it means it will be in the intersection also. So we can say that this set is closed with respect to addition. Now the second property, we will show that the W1 intersection W2 is closed with respect to scalar multiplication. Again, take any element, because W1 and W2 are subspaces. So X is in W1 and X will be in also W2, because W1 and W2 are subspaces of V, and if we have K as any scalar, so Kx will be in W1 and Kx also will be in W2. So we can say that this Kx will be in the intersection set, or we can say that this set W1 intersection W2 is closed with respect to scalar multiplication. So we show that W1 intersection W2 is non-empty and it is closed with respect to addition and scalar multiplication. So we can say that this W1 intersection W2 is a subspace. So in general, we can say that if suppose we have n subspaces of a vector space V, the intersection of all these subspaces will be again a subspace of V, and we can prove this theorem on the same steps as we have proved for two subspaces. So but the same situation is not true for the union. So what we have proved here, suppose we have this our vector space V, this is our vector space V, and suppose this is our subspace W1 and W2. So we show that this intersecting part W1 intersection W2, it is a subspace. But this is not true in case of union. Means what? Again, suppose if we have a vector space V, and if suppose there are two subspaces W1 and W2. So if we take the union, so union means these whole set, this whole shaded region. So this is your W1 union W2. So it will not be a subspace. So let us see. So we will see with the help of an example. Suppose we have a vector space, we take a vector space V as R3, and if we take W1 is the set of collection of all elements of the type raise any real number. So this will be a subspace of R3. You can check it very easily. Zero element, because A is a real number, so it can be zero. So zero element is there. So it is non-empty. If you take any two elements of this type, so their sum again will be of this type. And if you take the scalar multiplication, it will be again in W1. That means W1 will be a subspace of R3. Similarly, for you can take W2, the collection of all elements of this type, where B is again a real number. So same scenario is there. So it will again be a subspace of R3. Now if we take its union, so it will be the collection of all elements of the type. So we will check that this is a subspace or not. So take any two elements, because these two elements it is in union. So suppose our x is coming from W1 and suppose y is from W2. So that means x will have the form as, for example, a1 comma 0 comma 0, and y will have the form of the set, because W1 and W2 are defined like this. Now if you take their addition, x plus y, so it will be component wise addition. So you have first component a1, first component 0, so their addition will be a1 plus 0, means this is a1. Similarly for the second component, if you take, this is 0 and this is b1, so 0 plus b1 means again b1, and 0 plus 0, it is 0. So x plus y will be of this type. Now if you see this element a1 b1 comma 0, so this element is not in W1 union W2. Why? Because the elements in W1 union W2 is of the type either a1 a comma 0 comma 0, or of the type b comma 0 comma 0. So but here we have on both slots non-zero entry or the elements, so it will not be in W1 union W2. So this W1 union W2 is not closed with respect to addition, so it is not a subspace. So we see that union of two subspace is not a subspace, but there is a condition. If that condition is satisfied by those vector subspaces, then we can say that that vector space, the union of two subspace will be a subspace again. So let us see that condition. Suppose we have a vector space V, and we have subspace, suppose this is W1, and we have subspace W2. That means the union of two subspace, if this is our vector space V, and if it is supposed W1, and it is W2, then their union will be a subspace. That means the union of two subspace of a vector space is a subspace again if one is contained in another. Or you have this scenario, if this is W2 and if it is W1, then their union will be a subspace. So let us see, and this is the necessary and sufficient condition for the union of two subspace is again a subspace. Okay, so the union of two subspace of a vector space is again a vector subspace if and only if one is contained in another. Okay, so let us see its proof. This is quite natural. You can see it. So suppose that W1 and W2 are subspaces of a vector space V, then its union, then their union will be a subspace if and only if either W1 is contained in W2 or W2 is contained in W1. So let's see the converse part. That means suppose W1 is contained in W2, because W1 and W2 are subspaces, okay, and W1 is contained in W2. So if we take its union W1 union W2, so what it will be, because W1 is contained in W2, so it will comes out to be W2, and in the assumption W2 is a subspace, so that means this union will be a subspace. Or again, if we take the other part, this one, that means if W2 is contained in W1, so if you take its union W1 union W2, it will comes out to be W1, and W1 is again a subspace. That means this union is again a subspace. So either in any case W1 union W2 will comes out to be a subspace. So this implies that W1 union W2 is a subspace. Now let's see the direct part, which says that suppose W1 and union W2 is a subspace of V, then we have to show that either W1 is contained in W2 or W2 is contained in W1. We have to prove this thing. Now suppose to the contrary, if possible W1 is not contained in W2 or W2 is not contained in W1. So it means what? It means here if W1 is not contained in W2, so at least we will have one element in W1 which is not in W2. Similarly, if we have this condition, so we will have at least one element in this set W2 which is not in W1. Okay, so take such elements. So since W1 is not contained in W2 or W2 is not contained, so we can find an element X in W1 which is not in W2. or we can find an element y in W2 which is not in W1. Okay, so we have x is in W1 and y is in W2. So x is in W1 and y is in W2. So we can say that this x y will be in W1 union W2. So their addition will be in W1 union W2. So it means what? It means either this x plus y will be in W1 or x plus y will be in W2. So if x plus y is in W1 and we know that W1 is a subspace. So W1 is a subspace, and if you see here that this element x is in W1. X is in W1 and W1 is a subspace. So minus x, that means its inverse will be in W1. So and W1 is closed with respect to addition. So we can say that if we find out the value of these two addition of elements of W1, so it will be y and it must be in W1 because addition W1 is a subspace and it must be closed with respect to addition. So x is in W1 here, so its inverse will be in W1. So if we add two elements from a subspace, so it must be in the same set. So y is in W1. But if you see here that we have already taken that this we take this thing that y is not in W1, but here we are getting y in W1. So it is a contradiction. Similarly, if we take x plus y in W2, x plus y is in W2, and if you see here again that this element y, it is in W2 and W2 is a subspace, so there will be inverse of y, that means minus y will be in W2. So we have two elements x plus y in W2 and minus y in W2 also, and W2 is a subspace, so it must be closed with respect to addition. So just add these two elements, we will get it will be x, and this must be in W2 because W2 is a subspace. So but if you see here again, this x is not in W2. So we can say that this is a contradiction. So in both cases, we get contradiction. So we can say that either W1 is contained in W2 or W2 is contained in W1. Okay. So we have proved our result.